Hello dear students, welcome to channel and welcome to another new playlist of subject signal and systems. In this playlist we are going to discuss about Fourier series, Fourier transform, Laplace transform, Fourier series and Z transform. So basically we are going to discuss about the time frequency conversion phenomena and all the transforms or transformations which we required to make that phenomena possible, right? So we will be starting with Fourier transform. uh, this lecture will hold a little bit glimpse of the first chapter, the basics of signal and systems. So it would be nice if you have seen it, but even if you have not seen it, it's not exactly prerequisite for understanding of this lecture, although we might need understanding of that in upcoming lectures, but for today we're good. And also I will give you a little callback to the LTI systems as well, which we have learned in the very last playlist. Actually the whole last playlist was almost about the LTI systems. So from today on we're going to start the Fourier transform first. And if you want to check out the previous playlist, you will find those playlists in the description below, and I will also provide the link of one of the playlists in the I button here, so you can click on the top right hand side corner of your screen and go and check out that playlist if you are interested in it. Now let's start with the Fourier series first, right? And basically I'm not going to discuss, or I'm not going to cover that from the mathematics perspective. I'm going to cover the topic from the signal perspective. So if you're looking for so much mathematics here, I might skip some of the mathematical steps, but the emphasis here will be implementation of Fourier series or Fourier transform on my actual signal here. So uh, don't expect that I will be uh, performing the Fourier transform or doing the Fourier series summations in detail mathematically step by step here. Okay, so let's start. Firstly, we use a lot of mathematical tools for the analysis of both my system and signals. Either it is a CT system or DT system. And what tools do we analyze our system for? So we saw the system properties earlier. We saw if my system is static or dynamic. We check if my system is time variant or time invariant. We check for linearity, we check for causality, we check for stability, we check for invertibility, we check for frequency response. There are so many things we check for, right, in my system. So the question is, why Fourier series and why Fourier transform? How does it helps us with the analysis of my signal, right? So basically Fourier signal is used to represent any periodic signal in terms of complex exponential. And this complex exponential which I'm talking about are called basis functions. Okay, so they're nothing different functions. They're just basic sinusoid functions. And we take three different variables, uh, which we call my Fourier variables, or Fourier coefficient, either Fourier coefficient, right? So that's your Fourier series. Now coming to Fourier transform. So we use Fourier transform to represent any non-periodics or periodic signal in terms of complex exponential function as well. So Fourier series is for only periodic signals. but Fourier transform is for both non-periodic and periodic signals. And one more small interesting fact I'm going to tell you about that: Fourier transform of impulse response will be called the system function, and it will give us the frequency response of the whole system. So again, just like LTI systems, both CT-LTI and DT-LTI systems, impulse signal is going to be very crucial signal here as well. Now why do we need it? What is the necessity of this Fourier transform or Fourier signals? So firstly, all the signals cannot be fully analyzed in time domain only, right? You must need another medium. They can be analyzed in frequency domain, right? So this Fourier transform provides you that liability to shift from time domain to frequency domain, right? It provides you the time domain to frequency domain conversion of your signal, and based on that you can analyze your signal in frequency domain as well, right? Second thing, your signal is needed to be represented in terms of orthogonal basis functions, and we can do that as well with the help of Fourier representation. Third thing is the frequency domain analysis of LTI system, like say pole zero plots, your Bode plots, Nyquist plots, right? Your root locus, all those things, uh, and particularly this pole zero plots, we can obtain it with the help of Fourier representation, right? And the fourth term, the response of my LTI system for any deterministic signal can also be determined with the obtained with the help of my Fourier representation as well. So basically, the first highlight is we need Fourier representation for time to frequency conversion. If you want to move from time domain to frequency domain, you need to do either of these transformations, and based on that we will be able to jump from time domain to frequency domain. Now there is one important and interesting analogy between uh, periodic non-periodic and periodic and non-periodic signals, which go for the Fourier series and Fourier transform. Let's see how does that takes place. So firstly we divide our signal in two types, just like we did when we were doing the classification of my signals. So uh, the signal will either be a continuous time signal or it will be a discrete time signal. So by the way, if you don't know what continuous time signal or discrete time signal is, uh, you can check out the video which we have made in the initiation of signal and system coursework, which was the part of first playlist, so you can check it out. The link will be in the description, or the link will be in top right hand side corner of your screen in the I button, so you can check it out. Feel free to check it out. And now if you already know what continuous time signal and discrete time signal is, then you must know that both of these time signals, continuous and discrete, can be periodic and non-periodic signals, right? We have discussed about periodic and non-periodic signals as well, so I will basically just provide the link of the whole playlist in the I button, so you can check it out, right? So uh, continuous and discrete, both signals can be either periodic or non-periodic. So again, my continuous and discrete time signal will be either periodic time signal or non-periodic time signal, and those signals which are periodic time signals will go will be represented in Fourier series manner, right? We can take the help of Fourier series in order to make that transition from time domain to frequency domain. We can use Fourier series for my periodic signals. And for non-periodic signals, we always have Fourier transform, which is very uh, helpful and even faster. So we can do that for both continuous and discrete. For discrete as well, same thing will happen. The periodic signals will go under the Fourier series transformation, and Fourier series, and the discrete or sorry, the non-periodic signals will go through Fourier transformation, and by doing that we will be able to achieve the time domain to frequency domain um, shift, right? So that was the analogy between Fourier representation. Now let's quickly talk about the Fourier series representation of my periodic functions. So we are going to discuss about 2 to 3 periodic functions. First, we are going to discuss about the trigonometric Fourier series, or the quadrature Fourier series. So don't get confused by the name. This is the very basic type of Fourier series, and if you have taken calculus classes, you must have seen it, because it's very much famous. So most of you would be familiar with it, specifically if you have taken any calculus classes. So the formula is no different here. The formula is again the same. We have x of t is equals to a0 plus summation of k is equals to 1 to infinity a of k cos k omega 0 t plus summation of k equal to 1 to infinity b of k sin k omega 0 t. Now you all are pretty much sure about what other variables is, what other variables are, like you already know what is omega 0 t, right? You're pretty much already aware of all those things if you are following my lecture series continuously. So I'm not going to explain everything here, but these three terms, a0, ak, and bk, I told you earlier as well, we call these terms Fourier coefficients. So what will be the value of a0, ak, and bk? And this is not only for trigonometric or quadrature Fourier series. This is almost generalized formula for a0, ak, and bk. So the formula for a0 will be 1 by t integration within the time limit t, the time period actually, x of t into dt. When we do the same for a of k, the formula will become 2 by t integration within the time period limit x of t cos k omega 0 t into dt. So notice here that the term ak is with the cosine component of k omega 0 t, and the integration is taking place with again cosine component of k omega 0 t as well, right? So note this term for ak. Then we have bk, and for bk what will happen, the same formula as well. Instead of cos we will have sine, the rest of the terms will remain same. And again note here that for bk what is happening, we are having sinusoidal component here as well, and in the formula of bk we had the sinusoidal component of k omega 0 t as well. So that was the formula for trigonometric Fourier series or quadrature Fourier series, and this t is uh, integrating over the time period, which is basically nothing but 2 pi into f, right? You know what is the time period, 2 pi into f, or you can also call it 2 pi divided by omega. And basically we are taking integration of my signal x with respect to cosine or sine component of k omega 0 t, or uh, with simple dt. and we are finding my Fourier coefficients a0, ak, and bk. Now coming to the next type of Fourier series, compact trigonometric Fourier series, or we call it polar Fourier series. So here we are having a small change in our formula. Now x of t is equals to d0 summation of k is equals to 1 to infinity dk cos k omega 0 t plus 5k. Okay, so formula is x of t is equals to d0 plus summation of k is equals to 1 to infinity dk cos k omega 0 t plus 5k. And here what is d of 0, right? Because d of 0 is a new variable here, new term here, basically not a variable. So the d of 0's value can be given as, it is the same as a0 here, no change, but we are just calling it d0 for compact trigonometric functions or compact trigonometric series. We call a0 d0, and the formula also remaining same. There is no change in the formula as well. The formula is 1 upon t in integration over the time interval x of t into dt. The change here is the value of dk, right? We didn't had this term in the base form, but we are having it in the polar form. And how do we represent it? So dk is nothing but sum of ak square plus bk square, and we took the square root of it. And there is one more term, this delay, the phi k. Phi k is given as the tan inverse bk divided by ak. So that is the equation for your signal for your compact trigonometric uh, function, right? The third equation is exponential Fourier series. It holds simple formula. uh, Earlier we had 2 3 2 3 Fourier coefficient, but here we are having only one Fourier coefficient. See, what is the formula? X of t is equals to summation of k is equals to minus infinity to infinity x of k e raised to j into k omega 0 t, right? So which one is your only Fourier coefficient? Only Fourier coefficient is x of k. And what is the formula of x of k? The formula will be x of k is equals to 1 by t integration over time period xt e raised to minus j k omega 0 t into dt, right? That equation of x of k is also known as analysis equation because we use it for analysis part, and the original equation for x of t is known as synthesis equation, right? So x of k, we call it Fourier series coefficient. And uh, this hold analogy when we are converting x of t to my um, regular time series to frequency, sorry, time domain to frequency domain. We represented it by x of t to x of k, and we put a Fourier series symbol in the middle, right? So now why the exponential Fourier series is very good or very helpful? Because firstly, look, we only have to deal with one Fourier coefficient x of k. There is no other Fourier coefficient. Then the exponential form of Fourier series will give us double side spectrum, and that if when we have that, it gets very easier to understand it, very easier to study it. Third thing, that exponential form of Fourier series will represent signal in terms of complex phasors. So it is in its own way, it is very broad way of representation of your signal. And also exponential signals or exponential form can also be easily related to other representation, right? Like discrete Fourier transform. And remember, all the systems in practice right now these days are discrete signals. So we always use, not always, but for if possible majority of cases we use exponential Fourier series to make things easier. Now coming to the convergence of Fourier series, uh, in order to Fourier series to be convergent, your signal x of t needs to satisfy some of the conditions, and we call these conditions Dirichlet conditions, right? Dirichlet conditions are required to be satisfied in order to just satisfied by a signal in order to make the Fourier series, in order to converge my Fourier series. So the first condition is the single valued property. And what does that property says? The property says that my original input signal x of t must have only one value at any time instant within the time interval t0, right? So at time interval t0, for any time interval t0, it cannot have multiple values at same instant, right? If my signal will have multiple values at same instant, then you will not be able to make a call that which value is correct, and even if you do so, it will be very fuzzy, right? So we don't take multiple values of my input signal at same instant, and that condition is needed to be satisfied to make my to converge my Fourier series. The second condition is called finite discontinuities. And what does this condition says? It says that my input signal x of t should have at the most finite number of discontinuities in the interval t0, right? It should have most finite number of discontinuities in the t0 interval. The third one says the finite peaks. And what does this condition brings to the table? It says the input signal x of t should have finite number of maxima and minima in the time interval t0, right? So your maxima and minima cannot go from this to this to this so many times. And think about it, if that thing happens, if your maxima and minima so much if your maxima and minima are fluctuating so much, so many times, then it would probably make your signal a random signal. Your signal will not be a deterministic signal anymore. And when such things happen, then you will not be able to represent your signal with the help of any mathematical equation. So um, when your signal becomes random signals, you will not be able to apply any mathematical formula on your signal, and because of that, Fourier series will also be not applicable, right? Because Fourier series is a mathematical formula itself. It is having sinusoids and cosines in its formula. So finite peaks is the condition that my input signal f of t should have finite number of maximas and minimas in the interval t0. The fourth and the last condition is called absolute integrability. We saw this condition, or we this type of signal, when we were discussing the classification of different type of signals as well. So what it says my input signal x of t should be absolutely integratable. And we saw what is absolute integrability in the first chapter. And so if you are interested, I have already pinned the playlist link of first chapter in the I button, and also in description, so you can check it out there. Now I'm going to talk about the waveform symmetry. And basically what does this waveform symmetry indicates? That we have four type of symmetries in the waveform. You are already aware of even symmetry and odd symmetry. Now I'm going to talk about signal with zero mean. You're already aware about it as well, you just don't know it from my perspective. What is signal with zero mean? So when the waveform symmetry with respect to x-axis is your signal with zero mean, right? So we will check the symmetry of your waveform with respect to x-axis. What does that mean? That for such waveforms, the mean value will be 0, right? For such signals, the value of mean of your signal will be 0, and when such things happens, if mean is 0, which means my a0 will be 0. So that's your signal with 0 mean. The second one, which is called even symmetry, we already saw what is even symmetry and odd symmetry are in the first playlist and first chapter. So same as that, the even symmetry says the signal is even if my x of t is equals to x of minus t. Basically you have to satisfy that condition. If condition is satisfied, that means your signal is a symmetric, signal is holds even symmetry, right? For such signals, what happens, the value of b of k will become 0 for all the values of k, except for that the value of a of k will remain as it is. uh, by the term as it is, I mean it will follow the conventional formula. Then the third one is called odd symmetric signals, and again the signal will be called odd if the value of x of t will be equal to minus x of minus t. So again your signal has to um, your signal has to fulfill that condition in order to become in order to indicate odd symmetry in itself. And what's so special about odd symmetry is something that everybody likes it, because we don't have to do any so much calculation, right? Calculation part gets cut up. Why? Because the value of a of 0 and b of k will be 0 for odd symmetry signals. So you only have to calculate for a of k, right? Because a of 0 and b of k already are 0, so you just have to calculate for a of k, and the equation for a of k will remain uh, just the way it is, right? Okay, one small correction. The value of a of k and a0 will be 0, not b of k. Previously I said the value of a0 and a of k will be 0, and the value of b of k will remain as it is. It will sorry, previously I said value of a0 and b of k will remain 0, and value of a of k will be remain as it is. But actuality that will not happen. And actuality, value of a0 and a of k will remain 0, and value of b of k will remain as given in the conventional formula. So that is your odd symmetry. The condition for odd symmetry will be same as what I mentioned earlier. The correction was only in the part of a of k. And there is, more interestingly, we have the fourth type of symmetry, which is called half wave symmetry. So if two half cycles of my waveform are symmetric, uh, please notice that I'm putting more emphasis on half cycle. So if two half cycle of the waveform are symmetric, then your x of t can be represented with this formula: x of t is equals to minus x t plus t by 2, right? This t is your ongoing time, and this t is the time period, right? The time after which the signal will start to repeat itself, right? So this is t by 2, and we are taking t by 2 because we are taking half cycle. Because if it is symmetric, then you all know what happens with symmetry, right? The Mendel effect. So we are taking t by 2 here. And for such signals, what will happen, the value of uh, a of k will be 0, the value of a of 0 will also be 0, but the value of b of k will hold some value. But there is one more condition in that: b of k will hold some value only if the value of k is an odd value. If the value of k is an even value, that means b of k will also be 0. And when such things happen, we will all be happy, because we don't have to go through such all calculations, right? So uh, that's the half wave symmetry for you, and that sums up the waveform symmetry section. So we will keep this lecture till here, and most probably from the next lecture onwards we will be discussing the Fourier transform. If you have any doubts or any queries related to this lecture or any previous lectures, you can mention them in the comment section below. I will try to address them as soon as possible and as many as possible. Except for that, if you have any feedbacks related to channel or any suggestions, every feedback, every suggestion matters to me, so please feel free to mention them in the comment section below. I will try to address them, I will try to go through them, and um, I will be addressing them as soon as possible and as quick as possible. So I will be seeing you in the next time with the next lecture. Till then, goodbye and take care. Thank you for listening.